In section 4.5, we talk about integration techniques or substitution. So the following formulas provide a basis for an integration technique called substitution. We have that the integral of u to the r du is equal to u to the r plus 1 over r plus 1 plus c, assuming r is not equal to -1. The integral of e to the u du is e to the u plus c, and the integral of 1 over u du is ln of the absolute value of u plus c, or the integral of 1 over u du equals the natural log of u plus c, where u is greater than 0. Unless noted otherwise, we will assume that u is greater than 0. So recall the Leibniz notation dy dx for a derivative. We gave specific definitions of the differentials dy and dx in section 2.6. Recall that dy dx equals f prime of x and dy equals f prime of x times dx. So for y equals f of x equals x cubed, we want to find dy. So the first thing we need to do is find dy dx. And so that's just finding the derivative, which is 3x squared. And so dy, we just do 3x squared dx. Let's try another one. For u equals capital F of x equals x to the 2/3, we want to find du. So the first thing we're going to do is we're going to find du dx. Which is just capital F prime of x. Or we get 2/3 x to the -1/3. And so du is just 2/3 x to the -1/3 dx. For example number 3, we're looking at y equals f of x equals e to the x squared, and we want to find dy. So first step again is to find the derivative, or find dy dx. And so the derivative of e to the x, or e raised to anything, is itself, and then you take the derivative of the exponent, which is 2x in our case. And so that means dy is 2x e to the x squared dx. And so now we want to evaluate this integral of 3x squared times x cubed plus 1 raised to the 10 dx. So one thing we want to note is that we have the derivative of x cubed plus 1 inside the integral, right? Because the derivative of x cubed plus 1 is 3x squared. So I'm just going to rewrite this first. I'm going to put x cubed plus 1 raised to the 10th, and then 3x squared dx. And so now this is when we're going to bring in the substitution. So I'm going to let u the x cubed plus 1. And so that means that the derivative is 3x squared dx. And so using those two definitions, I'm going to rewrite the integral. So that's like the integral of u to the 10 du. And this is a lot easier to solve than what we started with. So this becomes u to the 11 over 11 plus c. But we know what u is. And so we just want to back substitute. U was x cubed plus 1. That's now raised to the 11th, and we divide the whole thing by 11, and then we've got plus c. Let's try the same idea with example number 5. We have the integral of 6x squared over the square root of 3 plus 2x cubed dx. And so we want to look at the pieces and see if we can find the derivative hidden somewhere in here. And so first, what I'm going to do is I'm going to rewrite the integral. This is 6x squared all over. I'm going to write the denominator with the 1/2 power. And so if we notice, the derivative of 3 plus 2x cubed is 6x squared, which is what we have in the top. So I'm going to let u be 3 plus 2x cubed. And so then du is 6x squared dx. And so rewriting our integral, we have 6x squared dx on top. And so that's what's going to replace and in the bottom we have our u. So let's go ahead and rewrite it. So we've got du on top, and on the bottom we've got u to the 1/2. And so we can rewrite this. This is like u to the negative 1/2 du, which will give me u to the 1/2 divided by 1/2 plus c. And then using keep, change, flip, that really gives me 2 times the square root of u plus c. And then back substituting, that's 2 times the square root of 3 plus 2x cubed plus c. Let's try example number 6. we have the integral of the natural log of 3x over x dx. And so usually u is the more complicated portion of our integral. So in this case, we would let u be ln of 3x. And so then the derivative is 1 over 3x times 3. And those 3's end up canceling, so I end up with 1 over x dx. And so what we end up having here, we could rewrite this so it makes a little bit more sense. ln of 3x times 1 over x dx. And so now we can just use the substitution. This 1 over x dx can be replaced by du, and the ln of 3x can be replaced by u. And so what we end up having is u du, which is u squared over 2 plus c. And then we just back substitute the value for u. So that gives me the ln of 3x squared all over 2 plus c. Example number 7. We have the integral of x squared e to the 4x cubed dx. And so the most complicated part of this looks to be 4x cubed. So I'm going to let u be 4x cubed. And so that means that du is equal to 12x squared. Well, that's really, really close to the x squared that we have in the original integral. It just has that 12 out front. And so the way that we can off balance this so we don't change the original is I can put a 1 over 12 outside of the integral. And then I can put the 12 in front, because the 12 and then 1 over 12 will end up canceling out and not changing anything. And so now that we've rewritten this in the correct way, we can replace the 12x squared dx with du, and we can replace the 4x cubed with a u. So this gives me 1 over 12 e to the u du. Well, this gives me 1 over 12 e to the u plus c. And replacing the u, we get 1 over 12 e to the 4x cubed plus c. And the last one. Now we have a definite integral. The rest of these were indefinite. So from 0 to 1, we want to find the integral of 5x times the square root of x squared plus 3 dx. So I'm going to rewrite this. That's the integral from 0 to 1 of 5x times x squared plus 3 to the 1/2 power dx. And so like I said before, the most complicated part tends to be the part we're going to let u be equal to. And so that x squared plus 3, if I were to take the derivative, I end up getting 2x, which is very close to the 5x that's out front, but we can fix it just like what we did in the last example. So we're going to let u be x squared plus 3, and we're going to let du be 2x dx. And so what we can end up doing is we can pull that 5 out front, and then we can put a 1/2 to offset the 2 we're going to put inside. And so 5 times 1/2 just gives me 5/2. We have x squared plus 3 to the 1/2, and then we're going to put 2x dx. And so we can replace the 2x dx with du, and we can replace the x squared plus 3 with u. So we really have 5/2 from 0 to 1. This gives me u to the 1/2 du. And so that's 5/2. And then we get u to the 3/2 over 3/2. And this will be from 0 to 1. And so this really becomes 5/2 times 2/3 u to the 3/2 from 0 to 1. Those 2's end up canceling. And we end up with 5/3. We can replace the u, and u was x squared plus 3 to the 3/2 from 0 to 1. And so we're just going to plug in. That's 5/3 times 1 squared plus 3 to the 3/2 minus 5/3 times 0 squared plus 3 to the 3/2. And so the 0 squared ends up canceling. We get 5/3 times 4 to the 3/2 minus 5/3 times 3 to the 3/2. And we're just going to get a decimal approximation here. This gives me 5/3 times 8. Minus 5/3 times 5.19615. And so this will end up giving me around 4.673.